Can everyone see my screen?
Yes. Yeah.
Yes, we can.
Okay, perfect. Okay, so good morning, everyone. Thank you for joining us today here as I present my research on electric vehicles and emergency evacuations, infrastructure challenges, and behavioral insights from an agent-based model. Now, just as an introduction, my name is Mohammed Babai. Just like Donya before me, as Jason said, I was a student until recently. I was getting my master's degree in transportation engineering at the University of Alberta. And I am now a research assistant under the supervision of Dr. Stephen Wong. To start with an introduction, the growing adoption of electric vehicles brings novel challenges such as their resilience during emergencies. Sometimes these emergencies are natural disasters. Damage to power infrastructure could cause outages, which would leave electric vehicles without fuel, while mass evacuations would put a lot of strain on the electric grid. So to better understand how to prepare EVs for these events, research on the unique behavior of these users is critical. Now, research on EVs in emergencies is limited but growing, but research on EV user behavior is even more scarce. So our aim here with this research is to focus on the EV user behavior, and this part of the research focuses on modeling EV user behavior using a simple agent-based model. So our main research questions in this section were: one, what is the EV evacuation time estimate for existing conditions in Canmore during an emergency evacuation scenario? Two, how do different EV charging behaviors impact electricity demand and charging station congestion over time? And three, what strategies and policies could alter EV charging station utilization, improve efficiency, and reduce wait times during an emergency evacuation? To answer these questions, we started with a survey of wildfire-prone residents of Alberta and British Columbia in the summer of 2023. After data cleaning and processing, we had 1,371 complete and usable responses. This let us develop an agent-based model, which we created using Python. The survey introduced the wildfire situation to respondents. The situation asked respondents to consider a situation where a wildfire is burning a few kilometers from your residence. The current temperature is high with strong winds and low humidity. You have access to an electric vehicle with 400 kilometers of battery range. Now, there were 4 different scenarios in this survey that were considered, but the EV section in this survey asked respondents to respond to the first scenario, which was how they would react in the scenario where they had an EV with sufficient charge. And so the question became, assuming your vehicle currently has enough charge to reach your potential evacuation destination, what is your initial charging action prior to evacuating? And their options were: 1, charge your vehicle at home to full battery; 2, travel to the closest charging station to charge your vehicle; 3, travel to a charging station that you expect will take the least amount of time to charge your vehicle; 4, not charge at all; and 5, other. So 41% of respondents said that they would charge their vehicle at home to full battery. It's also maybe important to realize that they were told that they had enough charge to reach their destination, so this might be a little surprising. This 25.2% of people said that they would travel to the closest charging station to charge their vehicles. 17.8% said they would travel to a charging station that they expected would take the least amount of time to charge their vehicles. 14.7% would not charge at all, and 1.4% chose other options. So with 204 EVs in the simulation, and I'll get to the specifications of the simulation in a bit, this led to 82, 50, 41, 29, and 2 EVs for each of the options respectively. The behavior of each of these options in the agent-based model was that the people who said they would charge their vehicle at home to full battery would begin charging immediately on the spot, no matter where they were on the layout of Canmore. Those people who chose the second option would find the closest charging station and travel to it. People choosing the third option would find and travel to the least time-consuming charging station, considering queues, charging times, and charging speeds. They would also recheck every 20 minutes to find the new least time-consuming charging station. People who chose option 4 would do nothing, and the people who said other were not modeled. Other specifications were that there were 204 EVs in Canmore, Alberta. This was from a census of a number of households in Canmore and the average EV adoption rate of Alberta. We used the current charging infrastructure in Canmore, which was about, I think, 12 stations. All EVs were assumed to have 400 kilometers of range and a 79 kilowatt hour battery, and it was assumed that they would all charge to 100% state of charge. We also assumed their initial state of charge to be a normal distribution with a mean of 50 and a standard deviation of 34.14%. We also assumed a minimum of 10% so that, as an assumption, all the vehicles could reach their evacuation destinations. We had 3 charger levels. Level 1 was 1.92 kilowatts. Level 2 was 19.2 kilowatts, and level 3 was 240 kilowatts. EVs traveled at 40 kilometers an hour to simulate traffic. While we didn't actually actively simulate traffic, we used this measure to account for any stops and waits and intersections. We had 3 alternate scenarios as well. Scenario 2 was all charging station EVs would charge at the least time-consuming charging station. Scenario 3 would be all charging ports are level 3 or 240 kilowatts. And scenario 4 was that we would assume there was 20% EV penetration in the population. The results of the agent-based model for the base model showed there was a significant spike in electricity demand within the first few hours. All EVs didn't complete charging in the first 24 hours, with many home charging EVs still charging after the one-day period was over. EVs choosing to charge at the least time-consuming charging station all would eventually charge at only one of 3 charging stations with numerous ports. In the alternate scenarios, we saw little variation in queuing and usage patterns. You can see on the graph up there, on the red line would be scenario 4, where 20% EV penetration was. You can see that the pattern is the same, just the volumes are different based on the number of EVs. However, we saw greatly reduced delays in scenarios 2 and 3. So as you can see on the table, the average delay per station went down from 180 to 6.5 in scenario 2 and 24.5 in scenario 3. Longest station queue went from 1341 in the base scenario to 21 in scenario 2 and 165 minutes in scenario 3. It is also important to note that across all 4 models, EVs did not finish charging within the 24-hour period, as you can see in the last row, where it was more than 1,140 minutes for all of the EVs, meaning it took more than 24 hours to charge every vehicle. Our key takeaways from this was that usage patterns across all models showed a significant spike that tapers down as more EVs finish charging. This was the same in the base scenario as it was in all the other scenarios where different assumptions were made. EVs choosing in the base scenario, EVs choosing to charge at the least time-consuming charging station all would ultimately charge at one of only 3 level 3 charging stations. So despite having access to more than 10 stations, people with that sort of behavior would only charge at one of the 3 stations, and this was because they had level 3 charging stations with the faster speeds, and they had numerous ports. Users charging at the closest charging station may be stuck in queues sometimes beyond 24 hours. So we noticed that people who did not change their intended destination for charging sometimes were stuck in queues beyond 24 hours. And increasing public charger charging speeds and assuming time minimizing charging behavior for all EVs, as was done in the scenarios, didn't significantly alter demand and charging queues. So this leads to our discussion, where the imbalance in charging station use suggests the need for improved distribution of infrastructure by adding stations, increasing charging speeds, or implementing real-time wait time information. We saw significant reductions in delay in the alternate scenarios, so these approaches could increase the availability of charging options and help reduce delays in real-time scenarios. We also discussed that consolidating level 3 charging into fewer higher capacity stations, distributing charging stations more evenly throughout the city, and encouraging all drivers to charge at higher speed public stations may efficiently meet demand. So one of the big reasons that the delay went on as much as it did across all scenarios was that a significant portion of people charging chose to charge at home. And because home chargers can only go up to level 2, and there's only so much that they can, so much energy they can deliver in such a limited amount of time, it led to a lot of delays. So encouraging people to perhaps charge at higher speed charging stations would help improve delays and make the system more efficient. We saw when the spike dipped, as we saw in the graphs, that was when most people using the charging stations were done charging, and so those charging stations in the simulation were left vacant, while people who were choosing to charge at home continued to have delays beyond 24 hours. evenly charging distribution chargers throughout the city would also allow people to access it more efficiently. They could get to the charging station that they need as soon as they need to, and there would be less delays, less queues, and increasing the speed of these stations would also increase throughput, number of EVs going in and going out within an hour. We also found that future research can focus on testing combinations of alterations. So maybe combining the higher speeds with also the more stations and the higher penetration rates, finding how these different effects combine to lead to different scenarios and different predictions for us. We could also incorporate traffic simulations to have a better overall understanding of the traffic of the area. Because in this simulation, we used the 40 kilometers an hour speeds just because we were not simulating traffic. And we could more accurately model dynamic charging speeds. So charging speeds in real life are very dynamic. They spike and they fall, and they are not the same throughout the whole charging process, which was not modeled in this model. So there are a lot of suggestions that we had for improving this simple agent-based model, but we found that the key takeaways from our model helped understand what demand was going to look like, how it was spread spatially and also temporally, and it's a good stepping stone to further research with agent-based models to understand how this behavior could more comprehensively impact efficiencies and delays in emergency scenarios. These are our sources, and thank you. If any questions, I will take them.
Great, thank you very much. So we'll maybe take one question live, and then you can maybe answer the others in the chat. So JP Helverston asks, did the survey sample include those who currently own an EV? If not, how confident can we be in these hypothetical decisions on when and how people are charging?
Right, that's a great question. It did. We asked people specifically whether they owned EVs, whether they were interested in owning EVs, and whether they were not interested in owning EVs. Surprisingly, about a third of respondents did already own EVs, which was much higher than we expected. But this survey did ask everyone whether they currently own an EV or they didn't to answer these questions. It's in different research, we sort of go into how the behavior of, well, not fully, but in some aspects, we go into how the behavior of electric vehicle owners, people who currently own EVs and are making these decisions, how that differs from the behavior of people who are just making these, I guess, preemptive assumptions about how they would behave with an EV. So that is a valid point. And for the sake of the research, we just used all of the information that we had because we find that there is value to how people would behave, ideally, in even how they would, I guess, self-describe their behavior without actually having the vehicle. We found value in how they would want to ideally use these vehicles, and it helps inform how people currently think about EVs and how they would be using them in an emergency scenario. I hope that answers the question.
Great. Yeah, so there's a few other questions for you in the chat. We'll move on to our next speaker, which I will actually present Donia's work at the end because I can sort of manage the time depending on how much time we have left. And I think it'll be easier than the recording. So our next, sorry, just give me 1 second. Our next speaker is going to be Dr. Terence, and again, I apologize for names, Dimatulak.
Dimatulak, yes.
Perfect. Who is currently a postdoctoral fellow at the University of Windsor. We're keeping our Canadian theme today, I guess. His PhD research focused on developing a framework to optimize charging station placement and estimate future electricity demand for long-haul battery electric trucks in Ontario, Canada. So he has expertise in freight analysis, spatial analysis, integrated urban modeling, preference experiments, and econometric techniques, and has contributed to real-world transportation projects and published in peer-reviewed transportation journals. So if you want to share your screen, and then whenever you're ready.
Perfect. Thank you very much, Jason, for the introduction. I just want to confirm, so can you all see my screen right now?
Yep.
Awesome. Again, good morning, everybody. Again, it's a pleasure to be here once again to be part of BTR conference. For today, I would like to share with you a part of my dissertation, which kind of look into the grid implications of electrifying long-haul trucking in Ontario, specifically by the year 2040. So as we have discussed earlier as well during the keynote presentation, we know that freight trucks contributed most of the GHG emissions in Canada. So as of 2022, it's about the total of 24% of transportation sector. And because of that, many believe, or at least like many thinks that vehicle electrification or freight electrification is a viable solution to do decarbonization for these vehicles. However, skepticism remains mainly because of the limited range as well as the lack of accessible charging infrastructures, mainly as well here in Ontario, Canada. So again, like, the term long haul varies greatly in the literature. So it varies from 320 kilometers up to 1,000 miles or like 1,600 kilometer per trip. And early studies suggest that in order to circumvent this limitation, simply increasing the battery capacity would alleviate the range anxiety. However, as we know, that simply increasing the battery capacity will also result into increasing the weight of the trucks, and increasing the weight of the trucks will also result into decreasing the maximum payloads of these trucks. So many of these carriers doesn't want to affect their payloads because it's going to affect their operations. So that remains in establishing or having like an accessible en route fast charging network as a prerequisite for the successful widespread of this electrification. So the impact of LHEV, so long haul electric vehicle charging on the electrical grid, has also not garnered much attention because as we can see the current technology, at least for electric trucks, it has about 5 to 16 times larger battery capacity as a typical passenger EVs. So this would result into a much higher impact on the grid, right? So having our attention or also focusing on the impact on the grid is also important once we have a widespread adoption for freight vehicles when it gets electrified. And this table just simply shows the list of at least current EV trucks that's in the market, or at least being introduced in the market. So these are the vehicles that I used in our study as a part of our estimation. So our overarching objective is to develop a modeling framework to estimate and evaluate the potential impact of charging LHEVs on truck movements and on the electrical grid, specifically in Ontario, Canada. So our focus is, when we talk about LHEV, the focus will be on a Class 8 truck only. So these are any trucks that have GVW rating above 15,000 kilograms or more. So in case of Canada, we have there's like a policy, or at least there's like a goal that they have set where zero emission transport aim to achieve a total of new vehicle sales. So the highlight here is just the sales. So new vehicle sales by 35%, of 35%, sorry, by 2030 and 100% by 2040. So what this means is that once 2030, once 2040 is reached, only trucks being sold, at least new trucks being sold, are going to be purely zero emission. But in our study, we assume that when we're talking about zero emission trucks, it's going to be battery electric vehicles. We know that there's also an alternative, which is like also hydrogen fuel cells, right? So, but here in our study, we're simply assuming that by 2040, 100% will be just like battery electric vehicles. So here we're just like showing our study area. So for those who are not familiar with Ontario, Canada, here we divided our study area into 49 census divisions. And we also highlighting here in the map, I don't know if you can see my cursor, highlighting that Highway 401, which is like one of the busiest freight corridor in North America, as well as Highway 400, which connects the southwestern Ontario to the rest of Ontario. So Ontario is the second largest province in Canada and also have quite a bit of cross-border bridges that connect to different states in the United States. And Ontario also has the highest number of registered heavy commercial vehicles in the country, according to Statistics Canada. And from there, we expect that the first to observe a significant number of electric truck adoption by 2040. So breaking down our objective, we try to answer these two research questions: is where should these en route charging infrastructure be located, and what factors and how they, beyond those commonly considered, impact the effectiveness of the regional en route charging network. To answer that, we're using historical truck GPS data mainly to identify the typical trajectory or the typical route of the trucks and the locations of their usual intermediate stops. So when we talk about intermediate stops, it's either rest stops, typical gasoline stations, or other very non-depot kind of stops to help us determine any potential locations for LHEV charging locations. So we highlighted here like the typical trajectory because we assume that regardless of the vehicle technology, whether it's diesel or electric, freight or carriers will still follow the route that they always go through, because that's pretty much like what the optimized route that they have, their typical operations will have. So from there, using this GPS data, we found that there's about 186 candidate locations that can accommodate these charging stations. And we also use historical truck flow data, so commercial vehicle survey for Ontario, along with truck ownership data, which is Polk data, to estimate the total number of LHEV trips. So not just the trucks, but like the trips by 2040. So here's the locations of these 186 charging locations. So as you can see here in my cursor, it makes sense that along Highway 401, there's a lot of en route charging stations that's going to be, because that's where the typical, I guess, like intermediate stops there will be for trucks. And one of our studies is also founded in many assumptions, but literature-based assumptions. One of which is that building and designing charging and grid infrastructure can take up to more than a decade. So that's why we chose the year horizon of 2040, because unlike passenger vehicles, establishing charging infrastructure for trucks would require a much, I guess, like heavier infrastructures or a much larger capacity grids in order to support these charging locations. And also long-term implications for battery technology's rapid progression, as well as the deterioration for the battery as well, is also considered, because it's not currently being considered in the literature. So that's like one of the gaps that we're trying to fill. And also, we also considered the auxiliary use, specifically the HVAC and the reefers. So reefers here is just the freezers. So when the trailer is being used as freezers, as well as weather variation and others that will affect the operating range of these LHEVs. And from here, we try to estimate the energy consumption rate for these trucks. And we divided the LHEVs into 3 different categories. So 3 different categories based on their energy consumption rate. So introductory LHEVs, so we're assuming that from the year 2023 up to maybe year 2030, this would be categorized as introductory LHEVs. And from year 2031 up to year 2035, it would be the emerging LHEVs, where we're assuming that there's much more different OEMs that are kind of adapting this technology. So there's much more choices for these trucks. And from year 2036 up to year 2040 is where mature LHEVs with much longer range and much more efficient will be present in the market. And we also use Canadian freight analysis framework in order to simply estimate the proportion of how many trucks are carrying dry trailers and how many trucks are carrying freezers or reefers. It's about 11% for that. And also, we are assuming that for the charging activities, we assume that all trucks are leaving the depot fully charged. at least 1 hour before their journey starts. And also they will seek, or they will try to find the charging stations if the state of charge of their trucks reach 20%, and they will be charging for 30 minutes until 80% state of charge is reached. So because of this very strict assumptions, where the charging stations, or at least the charging sites, will have varying levels of charging stations. So some of them are just going to be level 3 charging stations, and some of them are going to be megawatt charging stations, because we wanna maintain, or at least limit the disruption in the operations of these trucks, because we know that in terms of freight, right, it would be very crucial for them not to have any delays, and that would not be good if it's just going to be much affected. So it's going to be very difficult for them to transition if they know that their operation is going to be greatly affected. And so we try to limit it into just like 30 minutes per charging. And here we just kind of show you like how we kind of identify these charging activities. So for example, if a truck is leaving a 6 census division, so it's leaving full charge, and then if it reach 20%, now it's gonna look the nearest charging location until it reach 80%, and now it's gonna travel again until it reach 20%, and so on and so forth. So here, the first figure here, I believe this is the emerging vehicle, emerging LHEV vehicle. And as the technology improves, it's going to lead into a much longer range, which is like less charging activity. So in our optimization model, so I'm not going to bore you with the math that we did, but we used a flow-based path segment model to simply identify the optimal number for these charging locations that maximizes the total number of completed trips per hour for a typical day. And unlike earlier studies, we tried to capture the timing of the charging activities as well, based on the utilization rate, as well as the hourly electricity demand of each charging locations. In total, we kind of estimated like 63 scenarios. So for brevity, I'm only going to be presenting 2 of those because it's going to be quite a bit. And one of it is this map, where it's showing about 126 optimal locations during winter, if each of the stations are limited in a minimum of 8-hour utilization rate. So as we can see here, there's about 43 locations with more than that would require more than 10 megawatt electricity in order to function well. And on the other hand, there's about 83 locations that are going to be needing less than 10 megawatts. So we chose a 10 megawatt, I guess, breakdown is because we saw in the literature that typically a small manufacturing plant would require 10 megawatt capacity in order to support their operations. And that's very comparable to these charging locations. And here you would see the maximum capacity that's needed per census divisions. And this will be very helpful for different utilities to understand, or what would be the potential impact of these heavy duty, or at least like a high power demand charging locations in their specific jurisdictions. And here is another example, but this time we're only considering the space capacity. So this is during winter, but now the space capacity for the location is limited to only 50. So as you can see here, there's much more that's going to be needed, which is from 126 to 142 this time. But now we could see that Leeds and Greensville, as well as Durham, are most affected in terms of the electricity demand. As a conclusion, we found that winter, as expected, is much higher compared to other seasons. So status quo is just fall and spring, and compared to summer season as well. Also imposing a pragmatic utilization rate yielded promising results, as indicated by significant reduction in required charging locations to meet like almost 100% of these demand. And we found that only applying a maximum space capacity restriction have minimal effect in estimating the optimal number of discharging locations, as we've seen in the previous figure. And as a policy implication, these results can only serve as a basis because like any other future studies or any other projections, it's not really set in stone. But we could use this as a basis to establish a potential key locations, or at least to understand where these LHEVs are likely to travel. And we could also use these findings to develop a future energy management strategies, specifically for those different sets of divisions that can observe a high demand from these charging locations. And again, identifying areas where grid upgrades will be necessary in Ontario, and especially in winter, particularly those peak demands exceeding 10 megawatts, will also be valuable for them, like these results, I mean. And that's it. So again, like thanks for your time. Thank you.
Thanks, Chair. I'll maybe ask you one question. So Leonard's son's question is, what's your understanding of how far these long-haul battery electric vehicles can drive? And I've done some work on sort of this area, so I'm curious about this as well. Considering the temporal mismatch between driver schedules and charging schedules, right? So drivers have a certain schedule, and at least in the US, and in Canada, their hours are regulated. So how do you address that? And do we need autonomous trucks, or would that be, helpful to kind of address this mismatch?
Okay. I guess like for the first question, so the typical range for these trucks like vary greatly based on like what the OEMs are. So for the introductory LHEV, we used the estimated operational range from one of the case studies that NACFE did, which is about 320 kilometers. So they did a case study like in California, and that's kind of proven, according to them, that 320 kilometers is more than enough. For the emerging LHEVs, we use the average of all the available OEMs in order to just estimate, which is about 420, I believe. I forgot, but like, I think, yeah, sorry, 400, exactly 400. And for the mature LHEVs, so we assume that what would be the highest at this point, which is about 800 kilometers. And hopefully that kind of answers the question there. But like for the second question, like, do you mind repeating the second part of the question? Sorry.
Yeah, so there's maybe a mismatch between when a vehicle needs to be charged and the hours of service for a driver. Is there a need for, or would it be beneficial to have autonomous vehicles that don't, have these restrictions of hours of service?
Gotcha. For the first part, we did not explicitly consider the hours, because I believe in Ontario it's a maximum of 13 hours and an hour break. That's why we kind of also limited it into 30 minutes only. So at least it's not going to affect their operational hours. So I know that it's also going to be beneficial that there's going to be some kind of overnight charging to do that, but we did not consider that in the study. So we're simply just kind of considering that. And also our study area is just limited to Ontario. And we're actually expanding the study to consider a much longer distances. So because we know that trucks is not just within a specific provinces, right? So there's also cross-border trucks. So now in that regard, we're actually considering that, where there's going to be a much longer trips, or an possibility of overnight charging in that. And for the autonomous trucks, I cannot really answer that specifically. It's kind of like out of my expertise. I always believe, at least just my personal opinion, that it's kind of way far out there. So maybe not anytime soon, but I cannot really much comment on that, since that's not really my expertise of studies. Yeah.
Sure. So there was another question from Neil Ormos. Is there value seen in preferentially locating charging near Ontario's carbon-free electricity generation?
Ooh, that's a really good point. Yeah. Yes, of course. There's going to be there because one of the purposes of using alternative fuel vehicles, right, is to also diminish the carbon footprint, or at least like the GHG emissions. So by going there, or by like locating like in those areas, the electricity that are being produced, we can, I guess, almost guarantee that those are clean electricities. So that could kind of much amplify the impact of electric vehicles or electric trucks in this example, how impactful they are in reducing GHGs. Yeah, for sure.
Great.
That would be great to consider. Yeah, next time.
Yeah.
Yeah.
Great. So thank you, Terrence. Our next speaker is going to be Ping-Fan Hu, who's a research software engineer and PhD candidate in EMSE at George Washington University, supervised by Professor John Halverston. They do art development and data analysis in human behavior. And current research is on BEV ownership willingness to participate in smart charging programs, cost benefit of smart charging, grid integration, and an open source survey platform called SurveyDown, which I encourage everyone to take a look at. I know I have. It's very useful. So whenever you're ready, you can share your screen.
Okay, thank you, Jason. Let me think I will share. Oh, can everyone hear me and also see my screen?
Yeah, go ahead whenever
Okay,
you're
cool.
ready.
Great, yeah. Okay, so today we talk about the grid integration and smart charging. So Jason, you have introduced me. Let me just briefly introduce myself again. So hi, my name is Ping-Fan Hu, a PhD candidate at George Washington University, supervised by Dr. John Halverston, or JP Halverston. My research focuses on EV grid integration, consumer behavior studies on transportation, and research software development. So for more information, you can visit my website at pingfanhu.com. So let's get started. So throughout the past decade, the US market has witnessed a significant surge in electric vehicle sales, reaching about 10% of all vehicles. The BEVs, short for battery electric vehicles, takes the majority of them. However, the high ownership of BEVs have brought challenges to the grid. The unmanaged BEV charging is becoming a problem to the grid due to the spike. That's why we need managed charging to smooth out the grid load, as well as keeping the price low. The smart charging is a type of managed charging, which includes supplier managed charging, shortened as SMC, and vehicle to grid, shortened as V2G. For SMC, supplier managed charging is smooth out the overnight EV charger demand. So as you can see from the left, with unmanaged charging, the BEV load is easily passing over the capacity threshold. But with the SMC, electricity demand is controlled below the threshold. It reduces the peak demand and saves money. V2G is short for vehicle to grid. It is another type of smart charging that allows BEV owners to sell electricity back to the grid. So with V2G, BEVs become potential sources of electricity. However, the effectiveness of smart charging is really depending on the enrollment of the BEV owners. So there has been a few studies that looked on people's willingness to participate in smart charging programs, but they all have small sample size and also low EV ownership. Therefore, we aim to conduct a large-scale survey with high EV ownership to study the heterogeneity of BEV owners' preferences. Here, we have two research questions. Firstly, we want to know the sensitivity of each smart charging program feature. Secondly, we want to know under what combinations of these features would the BEV owners be more willing. So in order to answer these questions, we designed a conjoint survey to collect BEV owners' willingness to participate. Then we used the multinomial logic models to simulate the utility of each program feature. We use a platform called Formar to design the survey. It's not my own platform called SurveyDown because we designed SurveyDown later. But Formar is also an open source survey platform that supports R coding. In this survey, we have conjoint questions to ask for the willingness to participate. And then also the multiple choice questions to to collect the demographic information. But first, I want to explain what conjoint question is. So if I care about apples, I would want to know how people value type versus price versus freshness. So we have the three categories here. In this apple example, you can only choose one set of the attributes. So you have options 1, 2, and 3. So if you pick one option, you pick all the attributes in it. In short, conjoint is about forcing people to make trade-offs. Let's move on to the conjoint question for the SMC programs. So again, SMC is short for Supplier Managed Charging. These are the 5 attributes of SMC. You can see there are cache, override, and battery thresholds, and they all have reasonable ranges. For example, for enrollment cache, we have from 50 all the way to $300. And here is a sample SMC program. You can see that one-time enrollment cache, recurrent monthly cache, and how many times per month the charge can be shifted back to normal. The battery thresholds here are well designed to provide an immediate visual aid for the minimum battery and guaranteed battery. We also used mileage instead of percentage to make it more intuitive. The mileage will be shown according to the real values of each participant. This is the conjoint question designed for V2G programs. Again, V2G is short for vehicle to grid. The attributes are similar to SMC, but with some differences. For example, we have monthly occurrence instead of monthly override. The battery thresholds here are in the same layout, but since V2G drains the battery, the lower bound is how much the battery is drained to, and guaranteed battery is how much it is charged back to. There are 6 SMC conjoint questions. In each question, participants are provided with 2 valid options. Here we have option 1 and option 2, and also a not interested option. It is very important to have this not interested option because it is a validation of the willingness. When participants choose from these 2 valid options, they are surely to be interested in what they choose. Otherwise, they will choose not interested. Likewise, there are 6 V2G conjoint questions. So we collected in total of 1,356 complete filtered responses from Meta and Dynata throughout the year of 2024. And we made sure that all participants are real BEV owners. How did we do that? Well, this is how we did it. So in this car ownership section, we ask how many cars do they have. Then based on the number of cars, they need to select the make, model, and year of them. If at least one of them is a BEV, then we consider the participant as a BEV owner. So instead of asking if they own a BEV, this is a more reliable way. This is the showcase of the top 10 BEV models of a survey results. You can see that Tesla is the most popular brand, followed by Ford, Chevrolet, and some other popular brands. These results are also representative of the BEV market in the United States. Other than the BEV models, there are also some more important demographic information collected in the survey. So you can see most families have 2 cars. Most owners charge at home for more than 8 hours, and most of them care about climate very much. And more importantly, we have 100% of BEV ownership. The willingness to participate is quantified with the multinomial logic model, shortened as MNL. The utility of each option is a linear combination of the attributes, which is the Vj here, plus an error term, which is the epsilon j. The probability of choosing an option is the exponential of the utility divided by the sum of the exponentials of all the utilities. And also, we use the maximum likelihood estimation to estimate the utility. And here, the coefficient estimates plots of both programs, the SMC and V2G. Now, as you can see, the no choice has very high, like highest coefficient, which simply means that without compensation, users will just not participate. However, the coefficients alone are not enough to interpret the willingness. A more intuitive approach is the sensitivity, which means by how much the enrollment rate will change when the feature value changes. So this is one example of the sensitivity plots. As the enrollment cache increases, the user enrollment increases as well. The solid part is from the results, and the dotted part is the extrapolation with the model. And here we have a full demonstration of all sensitivity plots. The steeper slope indicates higher sensitivity. Also, as the feature values become higher, we see diminishing returns, but the solid parts are basically linear. So because the sensitivity plots are linear in the areas we concern, there is a convenient way to review the relevant importance of each feature. Imagine we want to increase the 5% of enrollment for each program. We start from a baseline and increase each feature value individually. Then we can see how much each one needs to be in order to achieve the 5% of enrollment increase. And here are our interpretations. So to start with, smaller value indicates higher efficiency, and recurring incentives are more important than one time. For example, in SMC, the enrollment cash needs to be 64.7 US dollars to achieve a 5% of enrollment increase, while for the monthly cash, the value is 3.2 US dollars. So monthly cash is more efficient than the enrollment cash. Same is true for the two types of cash in V2G. Also, guarantee threshold is more important in SMC than in V2G, indicating range anxiety. Finally, monetary incentives are valued more in V2G than in the SMC. This indicates that BEV owners are willing to leverage the BEVs as a source of income. So after the analysis of all these individual features, we could combine them into programs. We call them scenarios. I want to emphasize that the purpose of doing all these evaluations is to wisely allocate the resources of the grid because the resources are limited. Therefore, we need to maximize the enrollment of each program with the least efforts. Here, for the SMC, we have 3 scenarios. They are flexibility, recurring cash, and one-time cash designated. As we can see, for SMC, flexibility is highly valued, and recurring incentives are more important than one time. So due to the range anxiety, payment alone is not enough. There should be a combination of flexibility and monetary incentives. For V2G programs, recurring incentives are also more important than one time. So you can see here and here. But the flexibility is compromised since owners are willing to use the BEVs as a source of income. So the V2G programs are more incentive powered than SMC programs. Here we've made a smart charging enrollment simulator. We can play around with it and see the anticipated enrollment for each program. I can click on it, and yeah, this is the simulator. We have the about page and 2 more pages. So this is for the SMC. So we already have a predicted SMC enrollment probability because we have some base values. I can play around with the threshold. See? So the guarantee threshold matters a lot, but the minimum threshold doesn't do any change because so people are more caring about guarantee threshold. I can also change the cash. For example, I can change to 100 enrollment cash, and also I can increase the monthly cash. So the monthly cash has a larger effect on the final enrollment. I can do a reset button to reset back to the baseline. I can also play with the V2G, and likewise, we also have these sliders and also the values. Here, the monthly occurrence cannot be at 0, so it should be at least 1. So anyway, we can play with this plot so that we can estimate like what is the anticipated enrollment. So back to the presentation. So right now we have 3 contributions. So firstly, this is the first large N study of BEV owners' preferences for smart charging programs. Secondly, we quantify the sensitivity of BEV owners' preferences for smart charging features. And thirdly, we introduce the concept of attribute equivalencies. Remember the 5% example I showed to inform the incentive design. So these are the appendix for the logic model for SMC and also for V2G. And this is a reference list for this presentation. Thank you so much. So any questions? Oh, do I need, I think I need to reshare my screen too.
Yeah. Just a second. I don't see any questions. Just one comment that Kara Kochman points you to some papers by her former student Matt Dean, and JP is saying he's also an author on this study. So it's a small community, I think.
Yeah.
Yeah.
And also, if you guys are interested in my slides, this is the link for my slides.
Great. Thank you very much.
Oh, thanks.
Okay, well, if anyone has any questions, feel free to put them in the chat box. Our next speaker is going to be, sorry, just a second, Lin Su, who is a PhD student in transportation engineering at the University of Texas at Austin with Dr. Koppelman. Her research focuses on simulating EV charging demand using agent-based models and applying heuristics to site and size charging infrastructure for growing EV fleets and exploring the financial and environmental impacts of smart charging strategies, such as vehicle to grid, which we just heard about. She's also interested in shared micromobility and the application of machine learning techniques. And prior to her PhD at the UT Austin, she earned an MS degree from the University of Florida. So it looks like you're already sharing your screen. Feel free.
Just a quick note, Lynn is not here.
Oh,
This is the
right.
recording video.
Right. Yes. No, I do remember she sent me a message about that.
Yeah, she's actually in another Zoom room, so she
Right.
got scheduled. She's one of our tech coordinators like Matt. So sorry, guys. I'm here, but lots of the other people in this room can probably answer questions that come up too, because there are so many EV experts here.
Yeah. So let's play that recording.
Hi everyone, thank you for being here today. I'm Lin Su, a PhD student working with Dr. Carl Kochman at UT Austin. I will be sharing my research on grid integration of electrified transport, focusing on the environmental benefits, operational challenges, and fleet-level implications. As electric vehicles continue to grow in both personal and fleet sectors, it is important that we understand not just their potential for reducing emissions, but also the potential benefits when they connected to the power grid. This slide highlights the motivation behind my research. In the US, the transportation and industrial sectors together account for over 70% of NDU's energy consumption. As transportation transitions toward electrification, electric vehicles, along with automation and ride-sharing technologies, hold the potential to significantly reduce emissions. However, they also introduce new challenges by reshaping travel behavior and shifting energy demand patterns. At the same time, rising electricity demand from EVs, electric heating, and energy-intensive technologies like data centers is placing increasing pressure on the grid. For example, the Lawrence Berkeley National Lab reported that data centers consumed more than 4% of US electricity in 2023 and are predicted to consume over 10% by 2028. So this highlights the need for smarter grid management. One promising approach is to implement smart charging strategies like day-ahead charging and vehicle-to-grid (V2G) strategies, which can help manage EV charging with periods of high renewable energy availability, thus improving grid efficiency and reducing emissions. Despite this potential, there is still a lack of integrated studies that evaluate how electrified fleets, smart charging practices, and infrastructure investment together affect emissions and grid reliability. So here my work aims to address these gaps. The contribution of this work are threefold. First, we provide a comprehensive review of the environmental impacts of transportation electrification, while highlighting how emerging technologies such as EVs, automation, and shared mobilities are reshaping the energy use and emissions. Then we summarize the potential of smart charging strategies to optimize fleet operations, reduce emissions, and enhance grid stability. Third, we propose future research directions to bridge gaps in charging infrastructure planning, fleet electrification, and integration of renewable energy resources. The figure on the right presents a flow chart outlining the structure of this review. It begins with an overview of the transportation electrification trends, followed by a discussion of charging infrastructure planning strategies and common methods for siting and sizing EV charge stations. It then covers smart charging strategies and their impacts on grid performance, energy consumption, and environmental outcomes. The transportation electrification is accelerating rapidly, fueled by advances in technology, supportive policies, and financial incentives. In 2023, global EV sales reached 14 million, with major growth in the US, Europe, and China. Beyond the market growth, EVs contribute to substantial environmental benefits. They can reduce lifetime greenhouse gas emissions by up to 49% when paired with smart charging practices, and they are far more energy efficient than traditional ICE vehicles. However, the transition is along with challenges. The unmanaged EV charging could increase peak electricity demand by up to 50% by 2035, adding pressure on power grids and charging infrastructure networks. To address this, planning charge station and encouraging smart charging is important. Looking further ahead, the shared autonomous electric vehicles (EVs) offer even greater potential for sustainability, cutting per trip energy use and emissions while reducing the overall fleet size by potentially replacing more than 5 privately owned vehicles. This slide presents a comparative table of carbon dioxide emissions across transportation modes measured in either vehicle or passenger miles traveled. It highlights how vehicle type, fuel source, and occupancy significantly affect emissions. For example, the gasoline cars in the US emit around 0.77 pounds of carbon dioxide per vehicle mile, while plug-in hybrids and battery EVs emit significantly less, which are 0.57 and 0.44 pounds respectively. The air travel stands out with the highest emissions per passenger mile, especially in the first and business class, which have larger seating footprints. In contrast, e-bikes produce just 0.05 pounds per vehicle miles traveled, making them the most carbon efficient option for short trips. Among shared modes, ride-hailing service in the North America emits about 0.75 pounds per passenger miles traveled, whereas those in Europe, where EVs use is more common, emit only 0.43 pounds per passenger miles traveled. The public transit also shows meaningful variations. The electric buses emit less than diesel buses, and electric trains are cleaner than diesel ones, especially when powered by low carbon grids. Building on the environmental impacts and emission discussed earlier, the effective development of charging infrastructure is important to support widespread EV adoption. The flow chart shown here illustrates a common planning framework for siting and sizing EV charge stations, as seen in much of the recent literature. So this process begins with gathering a range of inputs from spatial factors like land use, road networks, and point of interest to social economic data such as EV adoption rates and household demographics, as well as grid-related parameters like local power supply capacity. So these inputs inform key constraints, including location availability, zoning rules, service quality targets, and grid limitations. The objective normally is to balance the cost efficiency with system performance, minimizing total costs while ensuring sufficient coverage, reducing user wait times, and improving environmental outcomes. A variety of optimization methods, such as genetic algorithms or GIS-based models, are applied to determine optimal charger placement, plug configuration, and expected system performance. So following the broader planning framework, these slides focus on specific siting strategies for EV charging stations that can improve access, reduce infrastructure costs, and enhance overall system efficiency. A key approach is shared charger access. For example, opening private chargers at electric bus depots, households, or multi-unit dwellings. So this shared use mode can maximize charger use, reduce congestion at public charging stations, and help address residential charging gaps, particularly in dense urban areas. Another important strategy is co-location, which integrating chargers with existing infrastructure, such as street lights, parking lots, public train stations, gas stations, and workplace. So these options lower development costs, make use of existing electrical connections, and improve convenience for drivers. Finally, building fast charging corridors along highways can support long-distance EV travel by minimizing downtime and range anxiety. Besides planning strategies, various approaches have been developed to support EV charging station siting and sizing. Each has its own strengths and limitations. So this table categorizes the approaches into five main groups. The optimization-based models, such as linear programming, offer optimal solutions under defined constraints, but it become computationally expensive for large networks. The heuristic models, like genetic algorithms, overcome this shortage, but they do not guarantee global optimality. The geographic model, such as GIS or clustering models, enable spatial analysis and intuitive visualization, but often overlook grid capacity and behavioral dynamics. Meanwhile, the simulation-based approaches can capture system-level interactions and allow for scenario testing, but require significant computational resources. Lastly, the machine learning techniques are promising for demand forecasting and behavioral modeling, though they rely heavily on large, high-quality datasets. Selecting the appropriate methods depends on the planning goal, data availability, and problem scale. Once charging infrastructure is properly sited and sized, how EVs interact with the grid becomes important, especially as electrification scales up. EVs typically interact with grid by three types of modes: V0G, uncontrolled charging; V1G, which is managed unidirectional charging; and V2G, the bidirectional charging, where EVs can also discharge energy back to the grid. Smart charging strategies like V1G and V2G can significantly reduce emissions and alleviate pressures on the grid by shifting charging to off-peak periods or aligning with renewable energy availability. Notably, V2G have been shown to mitigate residential peak loads by up to 75%, providing a powerful tool for demand flexibility. It also supports net zero energy goals, emission goals, and stabilizes electricity prices by allowing vehicles to discharge energy during high demand periods. When implemented in EV fleets, V2G can further enhance system efficiency, cutting greenhouse gas emissions by up to 35.8% and reducing energy consumption by over 40%, making it a high-impact strategy for sustainable mobility. Beyond environmental and grid-level advantages, V2G also brings substantial operational and economic benefits, especially for fleet applications. For example, as EVs participating in V2G programs can generate up to more than 2,200 in annual value per vehicle, while cutting the fleet charging costs by at least 10%. Implementing smart charging strategies like multi-stage day-ahead charging can further enhance efficiency, reducing peak demand by 38% and lowering daily carbon dioxide emissions by over 43 kilograms per SAEV. In real-world developments, such as in Shenzhen, V2G systems have successfully delivered 20 to 40 megawatts of flexible power to the grid without disrupting fleet operations, demonstrating strong potential to enhance grid resilience. However, despite these promising outcomes, widespread V2G adoption still faces technical limitations and challenges, which must be addressed to unlock its full value at scale. While current research has shown the benefits of smart chargings and V2G strategies, there are still important concerns need to be addressed moving forward. One key direction is to integrate infrastructure planning with dynamic fleet sizing, using tools like system dynamics modeling to better capture appropriate fleet size in response to changing travel patterns, social economic conditions, and charging behaviors. Another revenue involves understanding behavioral shifts and environmental trade-offs in emerging mobility systems, especially as we move towards a mix of human-driven, electric, and autonomous vehicles. Studying how traveler preference and mode shifts interact with charging demand will help us design more responsive and sustainable systems. Advancing transportation electrification will also require more integrated planning between the power grid and charging infrastructure. Rather than treating them separately, future studies should jointly consider private and fleet charging demand, grid hosting capacity, and the optimal siting and siting of charge stations to ensure system-wide efficiency and reliability. Lastly, as EVs are introduced into ride-hailing fleets, it is important to evaluate their penetration rate compared to traditional ICE vehicles within the fleet and the varying service demand and grid constraints. Optimizing fleet composition will help clarify the operational, environmental, and economic impacts of EV development across different future adoption scenarios. Thank you, everyone. This is the end of my presentation. Due to a scheduling conflict, I'm unable to present this work in real time. If you have any question or feedback, please feel free to reach out to me via email shown here. We also have several publications related to electric vehicles, energy system, and emissions, which are accessible through the link provided on this slide. Thank you all.
I'll thank recorded Lynn. I know Kara responded to a question in the chat. Are there any other questions for Lynn or? Okay, well, I think we can move on to our next presenter is Leonard Sund, who's a doctoral researcher at the Faculty of Management, Economics, and Social Sciences at the University of Cologne, where he conducts research on sustainable mobility under the supervision of Professor Wolfgang Ketter. He has a BSc in economics from Freie Universität Berlin and an MA in Economics Law and Social Sciences from the University of Erfurt. He was awarded a doctoral scholarship from the Cologne Graduate School in Economics, Management, and Social Sciences, and started his studies in 2021. And his research focuses on different aspects of electric vehicle in the mobility transition, such as adoption and charging coordination, and using diverse methodologies, including econometrics, optimization, and simulation experiments. So if you'd like to share your screen, Leonard, and start whenever you're ready.
Great. Are we good? Can you hear me? Can you see me? Can you see my screen?
Yep.
Yeah, perfect. Well, thanks for the introduction, Jason. Honestly, I'm kind of embarrassed. I didn't expect you to read out the whole thing. So yeah, again, hi, I'm Lenny Sund. Great to be here. Thanks for having me. I'm gonna present our paper, Coordinating Competing Electric Vehicle Fleets, which is shared work together with my colleagues from University of Cologne, Yannick Muiris, Ramina Hadi, and Wolf Ketter, as well as Konstantina Valugiani from IE Madrid. So first, to just put it out there, I don't really like cars. They stand around most of the time doing nothing, thereby like being quite good at jamming up inner cities. Most of the time when they drive, if they don't stand around, there are like relatively few people in those cars. And they like, due to inner city congestion, cost the average person in cities a lot of time every day. So in my perception, there are ample reasons to shift this kind of private vehicle-based mobility systems more towards systems where we rely on, shared vehicles or maybe pooling next to other mode shifts that may occur. So if we go to a more sharing and pooling-based mobility system, this will definitely increase the proportion of trips that are served through fleets of electric vehicles. And also, besides that, electric fleets will definitely be a relevant part of future urban mobility systems. So, I mean, first of all, as most of you likely know, the transport sector accounts for a very large amount of global greenhouse gas emissions. And a quite relevant part of that is attributable to private road passenger transport. So partially due to policy addressed at fixing that issue, we see skyrocketing adoption of electric vehicles, and already today some substantial amount or proportion of overall vehicles are parts of commercial fleets, and hopefully this proportion, at least in my opinion, will increase further when we have maybe a more sharing-based economy for that. So if we move to more fleet-based mobility systems, of course, a relevant question is how do we actually charge these fleets? And in the literature, I would say two pillars have emerged. So the first one, which is the more common one found, is that basically fleets own and operate their own charging infrastructure. So assumptions that we have in the literature here is often basically that they are, as we also have just seen, free to determine siting and sizing, which then, of course, they can, do in a way that is very beneficial to their operations. And also more importantly, probably, is that they are free to schedule and dispatch their vehicles to charge in an optimal way for their operations without anyone else interfering by also wanting to charge at their station. The downside to that, of course, is that the fleets have to shoulder the investment costs themselves. And generally, we consider that if you build up this capacity, you need more charging station per vehicle on the road on average. And another thing related to this is also that maybe cities also have an incentive not to just let commercial fleets plaster the entire inner city with their own charging hubs. The other pillar of thinking about how fleets charge their vehicles usually is that they just go ahead and charge at some random public chargers. Of course, this has the advantage that the fleets do not need to buy their own infrastructure. On the other hand, this could have substantial downside to the operation, as you have some uncertainty that you don't really know. So even if you would know whether or not the charges are occupied at the moment where you dispatch your vehicle, you do not know if anyone else beats you to that. So maybe you have to queue up for some time, and particularly when compared to, owning your own charging infrastructure, maybe you face significant markups in price for charging. So what we did was we thought, okay, maybe we can alleviate some of the drawbacks that are associated with either mode of charging. After some animation, we asked, okay, can we maybe do something about this? And in a similar sense as what I argued for before, where we may increase the efficiency of systems through charging before in the vehicles that we use, but also here is we wonder, can we coordinate these charging vehicles on a shared charging infrastructure? And in many cases, the most efficient coordination can be achieved by, we have perfect information sharing, we know the utilities of all the fleets of all the vehicles, and then we just have some godlike social planner entity that allocates the vehicles perfectly to each charger. But as you can also see from the title of this talk, a lot of times we see fleets that are in competition to one another in some degree or the other, sometimes more closer, sometimes not. So often they are not particularly willing to share their information. So we need some system that preserves privacy of relevant information of these firms. So the way economically minded people often think about this is they basically just slap a market on it and call it a day. So we ask, can we address the coordination problem of competing fleets charging at the same infrastructure using capacity auctions? The system we imagine looks kind of like this, where we say, okay, we have these fleets who go ahead and do their business, drive around, thereby they will deplete their battery. And then they have vehicles that are low at a given time and at a given position. And throughout the cities, then there are charging hubs or single chargers that are operated by a charging station operator, which also acts as an auctioneer. So the way we think about it is there's basically for every time t where there is capacity at charger I, the charging station operator will post the capacity that is there, which the fleets see. And then based on that and based on their charging demand, they will submit bids to the auctioneer, reflecting their wish to charge at a given station at a given time, which then are collected by the auctioneer, and the auctions are cleared. And so that in each of these auctions, the fleets will win some of the capacity and get allocated a charging reservation, which they are then, which is published to them such that they can plan their charging operations based on that. The kicker here is that we assume smart agents on both sides of this. So basically we have little robots sitting in the fleet central and at the auction central in a way that the clearing can happen in real time. And this is an important part. We have some time in between the clearing and the publishing of the results and the starting of the reservation period. This is important because then, of course, the fleets want to dispatch their vehicles and it takes some time for them to arrive there. And what is probably also relevant to note here is that as a simplification, because this is already complicated enough for us, we do not think about the energy charged here. So this is more like, okay, we have a limited amount of charges that are limited in time, so we auction off reservation slots in time and space. And then later on, the interaction with the electricity market probably will be more explicit. How we think about clearing this is we adopted a model that is akin to that of the electricity market, where we say we use uniform sealed bid auctions. That is, everyone for a certain location and a certain time will have to pay the same price. And then we, sort the bids by price and volume. And once the slots are all filled up, the clearing price will be equal to the highest rejected bid. And the advantage of this, if, for example, you compare it to Victory auctions, is that it's just computationally much more efficient. And recall that I said this happens in real time. This is relevant for this, where we cannot really afford to have like some maybe less gameable, but computationally much less efficient option. And in order to have a market that is as complete as possible, we say, okay, if there is any excess capacity at any station, we will just, as often as possible and efficient, auction off any capacity that is still left, such that we don't, for example, have like a charger just lying around for half an hour because there is just not an auction window happening at the moment. So we repeat this a lot, basically. And yeah, then we test this on a case study. Going back to what I said in the very beginning, this is a case study that is like relevant to our research interest, which is reducing the overall amount of private vehicles in inner cities. And as like maybe some of you from the general Austin area already have seen these numbers, that one shared autonomous electric vehicle can maybe replace up to almost 7 privately owned vehicles if we are lucky. So hopefully this is what's going on. So we do this using an agent-based urban mobility simulation. I will spare you the details now, but we compare 2 competing shared autonomous electric vehicle fleets. And particularly our case study is configured on data from the city of Chicago from 2022. We use demand data from ride-hailing services, particularly Uber and Lyft. And we place charging infrastructure throughout the city, which is derived from also a citing and sizing paper by our dear colleague Ramin. Important here is that there is not an outside option for charging. So basically fleets are only allowed to charge at stations allocated through this mechanism. They don't have depots. They cannot just drive somewhere and wait around in a queue for an hour. And our analysis timeframe is 1 week. We benchmark the following scenarios. So first of all, we have a private infrastructure case where for the entire charging hubs that we placed on the map, we just divide each in half, and like each of our 2 fleets gets half of the charges, and then they can just do whatever they want with that. And we they use like a myopic optimization that for every single time where they dispatch their vehicles, they minimize the overall downtime, which is driving, waiting, charging. Then we have a public infrastructure case, which is basically, we have all the chargers placed and there's no reservation, and we basically know whether or not the charger is taken at the moment we dispatch, but chance is that when we arrive there, it will already be taken. We are also currently working on the social planner mode that I also hinted at before, to just get that as an upper bound, even though this is not privacy preserving. And finally, we have the case I just pitched to you. And for some reason, we shoot ourselves in the foot here and have the coordinated case still use like a myopic heuristic for allocation instead of the optimization for the private infrastructure case, which we will change in the near future. So to some results. What we can show, you can see in blue here, this is the service level for our proposed case. Green is the uncoordinated shared infrastructure case, so basically the public charging case. In orange, you can see the private infrastructure case. And what you also see here is, as a benchmark, we have an unlimited charging case, where basically in every spatial unit in a city, we place 1,000 chargers. Just, you know, to show like the maximum theoretically attainable service levels. The service level here is the proportion of requested trips that are served. And what is probably important to note here is that user agents do have an outside option if the utility from taking a trip would be lower than their baseline utility, and this kind of means that then they would take a bus or walk. So what you can see here is that our proposed case is well able to compete with the private infrastructure case, even though for some reason we shoot ourselves in the foot and don't have it optimized. Both of these cases vastly outperform the uncoordinated charging case. And they are also relatively similar in utilization. And what you can also see, so here we have some graphs over time as well. What you can also see on the lower hand side is that even in the times where we have the lowest service rate, which will be the peak demand hours, the coordination case, that is our proposed mechanism, works better than the private infrastructure case. Okay, so just to sum it up, what we show here is that, like, as opposed to what is often assumed in the literature, we can have a competitive charging operation even if we use a public/shared charging infrastructure. And we also propose a privacy-conserving and computationally fast method of allocating this. And yeah, also we propose our multi-agent simulation, which yeah, we could also bore you a lot longer if you really cared about that. It's great. I would recommend it. It's gonna go open source at some point also, but this is not now. Yeah, we of course have some limitations. At the moment, we do assume, as I told you before, that people or fleets have to participate in the system. And of course, as I also hinted at before, at the moment, we also assume that we do not have exploitation in the auction mechanism. So this is also something, because this is not in its core an auction paper, that maybe will be developed in the future. And again, we are also still working on some improvements to the operations mechanisms, which will strengthen overall performance of the fleet. But we assume that our mechanism profits actually most from planning ahead more. So we hope that this will also improve in the future. And given this, there is some follow-up research that also emerges from that. So one question, for example, that is pretty interesting, at least to us, is how should fleets actually behave in these kind of auctions? Because even estimating what your value from charging at a given time and space is not exactly a trivial task. And then you also have the game of how you go ahead and participate in these auctions. And another interesting question related to that is, you know that you will be able to charge in like an hour, for example, in, I don't know, southern Chicago, then it will very well, it will be probably quite beneficial to you if you consider that in your trip assignment algorithm. So if you say, okay, you car, you're like already low to some degree, how about you take this customer to this location and then you can charge right afterwards. So this is also something we want to look at afterwards. And then also taking some inspiration from the electricity market, maybe extending the market framework to a longer time frame could be interesting, right? Then you could have also something like a day ahead market, because these companies often know relatively well in advance how their schedules look like, at least in a stochastic kind of sense. So basically you could clear that up front, and then when some stochasticity realizes and you already know, okay, now I have much more traffic in the north of the city, you can then sell off your your excess capacity in the south and get some more from the secondary market. So these are things that we maybe want to look at in the future. If you're interested in that or have some suggestions, we'll be very happy to hear that. If you want to take a look at the preprint of our paper, you can scan the QR code here. And yeah, if you would like to get in touch, please do so. We would be very happy if you're interested in that. And thanks a lot for your attention.
Great, thank you. So we do have a question for you from Neil Ormos. From the fleet operator point of view, does the auction present a high or even unacceptable risk that the price of capacity will be bid up to unreasonable levels? If so, does that create an incentive for the operator to invest in their own infrastructure for their own base demand and relegate their use of the capacity auction to excess or extraordinary needs? You can look at the question in the chat. But,
This is actually quite intricate. Where is here? So give me a sec. So basically, so first of all, is this a too high risk? That is actually kind of hard to say at the moment, right? It could be that the uncertainty associated with the prices is comparably high, but generally it should be assumed that in a market equilibrium, prices in auctions kind of converge to that what would happen in a posted price scenario. So I think, okay, I think we do have the problem that it may be the case, if not for some more auction side regulation, that if we have very high market power, for example, a large fleet like Uber could try to just buy up all the capacity and try to bully other fleets out of the market. And this may lead to a situation like the one hinted at. But in the auction literature, we often have these kinds of difficulties. And often these can be addressed by some auction rules and regulations. But I mean, this is not something that at the moment I'm well prepared to give you like a 1-hour math talk on how this would pan out. The idea that you operate a charging hub and then auction off excess capacity is actually a very interesting one that we have also already thought about in the past. And I think this is also something we will follow up on, right? Where you have this then relates to the literature on dual use goods, basically, right? Where you always have to consider, okay, will I now use this to charge my own vehicles, or can I maybe make a higher profit to rent this out to other fleets? So I think this is a very interesting point, and it's relevant, but I think there's definitely still merit for working on a market like this. Sorry for the very long answer. That was
Great. Well, if there are any other questions, feel free to post them in the chat box. But otherwise, we'll move on to the next speaker, which I will be presenting. So let me just bring up the presentation. Can everyone see my screen?
Yes,
Yes.
but you're not in slideshow mode yet.
Our introduction.
Oh, just a second. I think I have a version that has recordings in it. Just a second. How would I turn that off?
If anyone wants to provide suggestions, feel free to put those in the chat box.
Jason, if you would like, I have the PowerPoint with no recording, so you can just let me know when I go to the next slide.
Sure, yeah, we could do that.
There may be some animation within the slides, Matt, so good luck.
Yeah.
Maybe he'll just raise his finger each time.
Yeah.
Okay.
I think my room is
Or you can email it.
audio in here is crackling.
All good. Let me pull up the presentation.
Yes.
Hello, everyone.
Yeah,
Hello.
that's what I thought.
All right. Oh, I have the recording as well.
Yeah, but maybe you can mute yourself.
That's true.
Yeah, I can't mute myself and present it, so that's the
Okay.
challenge.
Nope.
So
That makes sense.
So I guess I'll give sort of my version of this presentation, which I must admit I haven't seen the presentation. So this was work that we did for Nebraska Department of Transportation under the previous administration. So yeah, next slide. And so under the Biden administration, there is an initiative called the Justice 40 Initiative, which said that 40% of infrastructure investments needed to go towards disadvantaged communities. And I think one of the main challenges with this, and here we're looking at the national electric vehicle infrastructure plans, is how do you define 40% of the benefits? So in our initial conversations, the state DOT would say, well, that just means 40% of charging stations are in disadvantaged communities. And well, maybe, but there's a variety of different benefits that we can look at. There's also kind of some questions around how you define a disadvantaged community, and Department of Energy and Department of Transportation and various different agencies had different maps and definitions of what they considered a disadvantaged community or census tract to be. And so that was kind of some of the initial challenges in this work. Next slide. Yeah, so like I say, there's a kind of a wide variety of different tools and maps and explorers created by different agencies that defined disadvantage scores in different ways. Next slide. So here's one example. So this is the ETC Explorer for the state of Nebraska, and you can see they define anything with the score greater than 64 in their system as being disadvantaged. So our objectives here were to develop a set of metrics based on data to analyze the impacts of EV infrastructure on transportation benefits and develop a framework that was generalizable to not just EV investments, but a variety of other potential investments as well. Next slide. So we did a bit of a literature review, and I think not surprisingly found charging stations are unevenly distributed, favoring higher income, predominantly white communities. There's issues around spatial access. There's a variety of different, equity measures, as I said, around data-driven tools, the Lorenz curve or Gini coefficient, spatial econometric methods like Moran's I-score, and then different ways of quantifying the benefits in terms of environmental, economic, energy, and health benefits, and how those are inequitably distributed. Also including job creation, improved air quality, and lower energy costs particularly benefit these communities. Next slide. So one part of this work was we did some public engagement. So we did a focus group with some community organizations, and then we also did a survey that we mailed out to residents across the state of Nebraska, and then sort of oversampled in disadvantaged communities to try to increase our sample in those communities. Yeah. So like I say, there's a variety of different tools that we looked into here. So there's A-Fleet CFI emissions, which looks at greenhouse gas emissions, carbon monoxide, NOx, COBRA, which essentially takes the A-Fleet outputs and converts those into health impacts in terms of emergency room visits, mortality. I think a lot of the the types of work that Dr. Hatzopoulou does in her research. And then there's the jobs EVSE tool, which estimates economic impacts in terms of jobs and earnings associated with EVSE or charging station investments. Next slide. And so when we can sort of map these different tools to different outcomes. So health is coming from COBRA, climate impacts are coming from A-Fleet, energy is sort of a custom calculation that we put together that's based on sort of the difference in energy consumption between traditional ICE vehicles compared with battery electric vehicles, considering energy consumption of each type. And then economics is in terms of job creation incomes, is based on the jobs EVSE tool. Next slide. And so given that there's kind of this wide variety of tools and metrics that we needed to sort of integrate into our work, there's a wide variety of data, and there's a significant amount of data preparation that Donia did in this work. Next slide. So the sort of overview of the framework that we developed is the first stage is demand prediction. What is the demand for EVSEs in terms of electric vehicle travel? And then what is the consumption estimate by census tract? And then what are the benefits measured in sort of their native units of energy, CO2 emissions, et cetera. How do we distribute those benefits? So I'll talk a little bit more about that process, and then converting this into a single kind of monetization. And then the last step is assessing that outcome in terms of equity. Next slide. So as I say, the first step is we did sort of a demand prediction using a fairly kind of standard S-curve market adoption framework. So that's just kind of giving an overview here. Oh no, my light's turned off. Next slide. And so then we can estimate intra-county and inter-county trips. So we did the analysis at the census tract level, but we had county level VMT data. So we do some kind of calculations around that, trying to infer those different totals. Next slide. And then converting that into from sort of total miles traveled to electric vehicle miles traveled based on county level EV registrations as of 2024. Next slide. And then, like I say, allocating those from the census, or sorry, from the county to the census tract. Next slide. So then we estimate total energy consumption, which is just a function of the number of charging stations, and the number of charging ports, the operational hours of the charging station per year, and some other details to kind of get a sense for the supply available of EVSE. Next slide. And then we estimate consumption, which here we've written as eVMT for electric VMT, but I know it's often also used for empty VMT. So that's that calculation there. Next slide. And then this is sort of the way that we distribute this. So we have this sort of accessibility measure. So the benefits of charging stations in a census tract sort of have this they have benefits within the census tract, but then they also potentially have benefits for the surrounding census tracts that dissipate as a function of distance. So if you live in a census tract that adjoins another census tract that has a charging station, even though the station isn't in your census tract, there's some benefit to you because you're going to drive to that tract and use the charging station there. Next slide. Yeah, so then we have this set of calculations that we do to calculate these benefits across different categories, so health, energy, emissions, jobs. Next slide. And then this is just a bit of a summary of what that looks like. So there's different emissions factors that go into this, energy content of different fuel types to calculate energy, but just to kind of show you, give you a sense for it. Next slide. And then this is for economy, which again is mostly based on the jobs numbers and then distributing that to different census tracts. Next slide. Yeah, so then, like I say, we have this sort of gravity-based distribution approach. And I should say there's definitely, some complications with this, right? So if you're looking at something in terms of jobs and you have a charging station in a high-income community, there's a good chance that higher income, those higher income residents are unlikely to be working as charging station, maintenance workers. So those benefits in terms of jobs are more likely to go to maybe a different tract that has a higher likelihood of that kind of labor. So there's definitely some complications and nuance to trying to sort of sort out these different benefits. Next slide. And then, like I say, we convert all of these, disparate unit benefits into monetization. Next slide. So this is just giving you an idea. Next slide. You can go to the next slide after this. Yeah, so what we're really interested in at the end of all of these calculations is this equity assessment. So we distribute these different benefits using, as I say, kind of a variety of different approaches, and go to the next slide. Yeah, okay, so this is, giving a summary of EV ownership. and then total vehicle miles traveled. So you can see a lot of it's concentrated around the larger cities in the east of Omaha and Lincoln. Next slide. You can go to the next one. Just in the interest of time, go to the next slide. I think we have kind of a summary. Yeah, so this is, summarizing some of these different benefits and how they vary spatially. Next slide. Energy benefits tend to be, yeah, perfect. Tend to be concentrated in areas that have EV owners. Go to the next slide after that. Keep going. I know that there's a slide here that I want to get to in just the last minute. Yeah, keep going. Here we go. So as I say, we do this kind of equity assessment, and we use a few different metrics, but one of the metrics we use is Morin's index, which lets us look at the spatial distribution of benefits, and whether they're clustered in a particular area, dispersed, or randomly distributed. Next slide. So this just kind of shows a map of that and then normalized by population. Next slide. Just go to the conclusion slide. Yeah, so perfect. So I think kind of the high level conclusion of this work is that based on kind of our calculations, we find about 19 to 20% of the benefits are reaching disadvantaged communities. So this falls short of the Justice 40 initiative, but I don't know that that necessarily says that that it's unsuccessful, because I think in a lot of ways this Justice 40 was really just sort of an arbitrary number, right? So if we add more communities to the list of disadvantaged communities, then that's going to be boosted up. There's no real connection there to population. So the population as a percent of the total is, and I don't recall the exact number, but it's lower than 20%, right? So these communities are getting benefits, but we also find that the majority of the benefits that we're calculating are associated with the energy benefits, which tend to be for higher income households or counties, I guess census tracts that can afford EV ownership. And then the health benefits that come from things like EVs driving through your neighborhood or job creation for charging stations tend to be fairly marginal, kind of compared with the energy value. Next slide. Yeah, so I think just in the interest of time, I'll leave it there. That like any study, there's limitations to this. Great. So I realize that we are at time now. If you have questions for me, feel free to post them in the chat box. I though have to switch to chairing a different session. So maybe if you have questions about the presentation, you can, I'll put my email in the chat box here. So thank you very much.